Assalamualaikum and good day. Today we are already in chapter 14. Based on the reference from the book of Mehmet Khanoglu. So we in the chapter 14. So actually, based on our teaching plan, we already in the chapter 11. Yeah, I guess we are still in the chapter 11. So to satisfy this chapter, we will conduct on the starting in the week 11. So we try to make a spread into two parts. The first in week 11, we will be talking about the farm, and then the second of turbo machinery, we will talking about turbine. Okay, let's check in the first part of the chapter. We will talking first terminology first before we go to understanding the farm. So we try to understand what terminology we will use, especially use in the turbo machinery part. Yeah? So actually, turbo machinery we will relate to the rotating mechanical work. Yeah. So if you know about farm and turbine, we will work into rotation work. Okay. So for example, we can see here engine jets on the modern commercial airplanes, highly complex turbo machinery machines that include both pump, compressor, and turbine systems. Certainly, we will see the turbine of jet engine will be involving both turbine and the pump in one machine. Yeah. So today in this chapter, we will discuss about four objectives here, as you see. The first, identify various types of pumps and turbines and understand how they work, and apply dimensional analysis to design new pumps or turbines that are geometrically similar to existing pumps or turbines. Perform basic vector analysis of the flow into and out of the pump and turbines. Use specific speed for preliminary design and selection of pump and turbine. So in the first part, in the pumps, we will also elaborate about various of pump. Yeah? We will see the classification and pump, and then how its application in the engineering. So you can see here we have analogy of pump and turbine. So you can see the first is the pump. You can see the figure where the come with the bigger diameter, and then come out with the reducing in the diameter. So if you see, you check in the figure of turbine, so you can see opposite will become input is small diameter, and then become to output bigger of diameter. So opposite before between the pump and turbine. So let's check the text here. What the pump means. Energy absorbing devices since energy is supplied to them, and they transfer most of the energy to the fleet. Usually, we are rotating shaft. The increase in fleet energy usually less fell as an increase in the pressure of the fleet. So you can see by of the increasing the pressure, so we'll be supplying the liquid after the pump. Yeah, so you can see the maybe will be increase the pressure after through the pump. And then about the turbine, energy producing device they extract energy from the fluid and transfer most of the energy to the some form of mechanical energy output, typically in the form of the rotating shaft. Typically, we try to utilize energy from the fluid to transfer energy into the mechanical work by rotating from the shaft. So the fluid at the outlet of the turbine suffer an energy loss, typically in the form of the loss of pressure. So we will see the pressure will be reduced after through the turbine. So the purpose of the pump is to add energy to fluid, resulting in increase in fluid pressure, not necessarily an increase of fluid speed across the pump. So the purpose of the turbine is to extract energy from the fluid, resulting in a decrease of fluid pressure, not necessarily a decrease of fluid speed across the turbine. So actually, we try to utilize, as I said before, we try utilize in the energy of the fluid from the system into the turbine to rotate and then become to mechanical work. But opposite of the pump, we try to convert mechanical work into the fluid energy. So that one is the opposite from the turbine and the pump. So let's we talk about the terminology that we can use in the some device in engineering. So maybe we will find someday maybe the term, what is the pump, the term of the fan, blower, and compressor. What is it? What difference between them? So the pump actually is for liquid. We try to transfer the liquid of fluid. So fan is only for the gas. So gas pump with the relatively low pressure, fast and high flow rate. So blower, a gas pump with relatively moderate to high pressure. So different with the fan and the blower is only pressure, but we still transfer in the gas of fluid. About the compressor is gas pump designed to deliver very high pressure. So between them is pressure. So fan is lower compared to other, and lower is a medium. So you can see in the table the comparison between the fan, blower, and compressor. So the pressure become higher from the fan and to the compressor, and the volume rate is different. Is opposite from the pressure. So you can see from the higher come from the fan, but become lower until to compressor. So blower still act as a medium of both pressure and the volume rate. Okay, this one is one of example of the pump, but this one is it's not considered a turbo machine because its pump is moving by transnational moving, so by piston. So this one is considered not machinery, turbo machinery. So let's take the text. Turbo machine, pump and turbine in which energy is supplied or extracted by a rotating shaft. But this one is no rotating shaft considered inside of the pump. So we cannot consider as turbo machine. So the word turbo machine and turbo machinery are often used in the literature to refer to all types of pump and turbine, regardless of whether they utilize a rotating shaft or not. Okay, this one is other example of pump, like our heart. This one considered a positive displacement of pump. So the term of positive displacement machine is fluid is directed into a closed volume. Energy transfer to the fluid is accomplished complies by movement of the boundary of the closed volume, causing this volume to expand or contract. There is sucking fluid in the oscillating fluid of respectively. So actually, we try to increase the pressure to moving the fluid. Yeah. So this one is dynamic machine. The term, other term relate to the turbo machinery. Yeah. Is about dynamic machine. Yeah? There is no closed volume, instead rotating blade supply or extract energy to or from the plate. For pump, these rotating blades are called impeller blades. So different between the fan and turbine, wind turbine. Yeah? You can maybe will be called similar. This one is impeller blade. Yeah? So this one considered dynamic because the pump is include pump and ducted pump and open pump. So actually this one is will work continuously. So that's why we can call as a dynamic here. Sometimes we can consider as a low velocity, and sometimes we can consider high velocity and medium. So this one is the dynamic condition. It depends on the supplying of this. Okay, now we after we introduce the terminology, now we go to understanding about the pump. Yeah? So what difference between the pump and the turbine, how to calculate the efficiency or designing required pump in certain condition system. Yeah? So sometimes the engineer needs to do design supplying of fluid, yeah, within one point to other point with the different conditions. Sometimes have high elevation or low elevation. So we need to design. So how much the pump power need to supply into the system. So that's why we need to design by certain conditions and with the boundary associated. Okay, let's check. Maybe before we learn about designing and the pump requirement, so maybe this one will be related to previous topics like the mass transfer or balancing mass, and then the number of the volume rate. Yeah, we will use frequently in this design. So you can see here we have formula of volume rate. This one is already known in the fluid mechanics. Also, before that, we also introduced in the thermodynamics how to implement the formula volume flow rate. Okay, this one also we are already introduced in the Bernoulli formula, where it's involving in the pressure, energy, kinematic, yeah, and then also energy from the potential energy. Yeah? So we can assess together in one Bernoulli formula. And then to calculate Bernoulli effect, remember final result is had to be in the unit meter. So the formula become, the final become like this, yeah, as mentioned in the slide. So you can see this one to calculate. So this one, when we calculate before condition through the pump, consider as in, and then this condition is after to the pump. So let's say the pump supplied with a certain length of the piping. So in the during this line of piping, maybe will be include so several component like valve, yeah, is a, and also other instrument like elbow, so anything will be considered, yeah, inside to reduce the uh, power supply, yeah, of the fleet. So we will consider in designing. So this one is considered when we try to analyze, differentiate pressure within input of pump after exactly of to the pump. So we can measure of the pressure. So if we try measure exactly on the exactly before to the pump and exactly after the pump, so we can measure differentiate between them, between this input and output by the formula. Simple, because we can cancel influence of diameter, because we will use similar diameter. If we consider the pump will supply similar diameter, because it's very near from the condition, so we consider Z in equal to Z out, unless we measure long far away from the pump. So maybe the pump already provide the piping system already, then we can consider the maybe elevation change already, and then the diameter change already. If we consider piping, yeah, provide piping after the pump. Yeah. That one is different condition. So this one is considered only different pressure. So we consider the calculation only remain H equal to P out, yeah, negative to P in, and then rho G, yeah, over to rho G. This one how to calculate, and then for efficiency we can ratio between the power water horsepower, yeah, with two shaft power. So how much supplying power into the pump. So actually the pump is separate within the motor. So the motor is energy supplying or mechanical supplying into the pump. This one is considered energy come out from the motor. So maybe motor considered in the electric motor, or motor in the injection, motor is made by a fuel motor. So we can consider that one is outside power supplying, yeah, into the pump, and then we can uh, measure how much the water horsepower to outside the pump. So from this comparison, then we can consider a efficiency of pump. Okay, you can see this one is how we calculate, yeah, within the power supplying or required, yeah, in that our designing. So after we consider with the head, yeah, after we calculate with the Bernoulli, and we involving with the head loss also because of the piping system and all instruments inside the piping. So then after that we compare how much the power need, yeah, to supply the system, and then after we provide the system with the motor, so the motor will be considered able, work in that designing. So maybe after we design, the supply should be 100 horsepower, and then we need the pump is more than at least more than 100 horsepower. Okay, so this design with the pump provide in the system, so we can separating, yeah. So we can call that one is required design as required, and then the pump supply engine power is other system, yeah. Then this condition pump, yeah, will be influenced by certain conditions like the flow rate, yeah, number of flow rate, speed, yeah. So different conditions. So this one will be influenced into the pump. So from this required designing, we will get the one line, yeah, that one we can call the shut off, yeah, shut off of head. So let's check the better. We will check the text here. For term of pre-delivery, the maximum volume flow rate through a pump occurs when its net head is zero. This flow rate is called the pump pre-delivery. So when head is zero, so it's easy to supply without any any outside of the power. So just do by himself. So because head is zero. But if head is more than zero, so we need to push or force the system to transfer the fluid. Yeah? So the shut off head, the net head there, so when the volume flow rate is zero and is achieved when the outlet port of the pump is blocked off. Under this condition, head is large but V is zero. The pump efficiency is again zero. So because of the pump is doing no useful work. So when we cut off the system, so what happens? No number or no amount of the flow rate. So this one is we call shut off head. But efficiency point, the pump efficiency reaches its maximum value somewhere between the shut off condition and the pre-delivery condition. Is noted by asterisk, yeah, with the head, the ST, and H. Yeah. Pump performance curve of H, efficiency pump, and BHP, which is horsepower, a function of volume flow rate, are called pump performance curve. So we can see how we plot the this relationship between the head with the flow rate. Operating point or duty point of the system in typically application have a target and head available. Make at one unique value of flow rate. So as I mentioned before, so we design, we call a head required, and then a pump itself head available, so we can supply. So that pump power, motor power, we call head available. So how much the available can supply? Yeah. So you can see between the head required to the flow rate, we can make a one curve, yeah, that will cross each other, and then that one is the point, the important point. Then we can utilize the number to use in the design. So you can see, yeah. Okay, this one, as I mentioned before, shut off head when the head is come the higher, and then no delivery, yeah. And then when the head is zero, delivery will be higher, as I mentioned before. So no more when head is zero is easy to transfer the liquid, yeah, of liquid. and then this one is power to efficiency pump to the flow rate. So you can see. So next is system of pump. Head retired. So with the head retired is our design. So design based on the flow rate number. So if we see head number will be increased by increase the volume rate, and then in the head available pump machine or pump motor, we supply by zero of flow rate will be have the high of head, and then by increase of the uh, this one flow rate will be decrease of head. So the red one is our designing, and then the blue one is motor or electric machine, the power that provides by supplying. So then we can meet the one point. That one is operating point, the important point. So this one is good to have good efficiency. Okay. Okay, let's see. One example, when we design, so the pump is the middle here, and then we provide a mass of the instrument inside, so we'll be contribute into the head loss. We have to already learn about this one. The mass of instrument will be increase of head loss. Yeah, so this one. So every part will be increase the head loss. So we design with the Bernoulli head, so we can get the head, and then we try to relate head into the power of the pump. So and then after we get the head, and then we transfer into the power supply of the pump. Yeah. So how much is based on the flow rate. Yeah, flow rate number. So we have an example here. So I go fast. Example, if we one is just repeat from the calculation of head. Yeah. Okay. In the calculation, in the head requirement, we need also to calculate the required net positive suction head. So how much the suction exactly in the input of head. So if the head is no suction, so consider the pump the below of required. Yeah? This one we how to calculate the head. Yeah? And PSH, yeah? Net positive power. Okay, I can go fast. This one is positive displacement pump. So we have several options in the pump classification about positive displacement. So actually the positive displacement is from suction to the push the speed to transfer. One consider as positive displacement pump. So we have several types here. And maybe how we try to supply by suction. That one is called positive here. This one is dynamic pump. Dynamic pump is by rotary impeller blade. Yeah. So the blade will be rotated continuously. So it's called dynamic. Then under dynamic, we have several types of pump. We have centrifugal, axial flow pump, mixed flow pump, and centrifugal pump is one example of centrifugal pump. You can see the supplying is through you can see the direction. Some will be similar axis of the shaft. This one is radially of the shaft. One is radially. So example how to calculate the shaft of the radial of pump. Axial pump. So we use same blade that provide in the airfoil. We have a contour similar from the airfoil. Water plate is here. Okay, one is engine turbine object engine. You can see we have compressor in the front of the engine, and then we have turbine in the back of the engine. The time to calculate. Then we go to calculation in the pump scaling law. So in pump scaling law, actually we try to understand about turbo machinery provide a very practical example of power and usefulness of dimensional analysis. And then we try to apply the method of DPT variable to the relationship between gravity times that head and pump properties such as volume flow rate. Some characteristic length, typically the diameter of impeller blade, and so on. So we try to calculate all the parameters by head coefficient, capacity coefficient, and power coefficient. So to determine the pump is efficient or not by these coefficients, head coefficient, capacity coefficient, and power coefficient, this formula. So to calculate the performance of the pump. So we call the pump scaling law. So by dimensional analysis, so we have dimensional analysis. You can see here our parameter is dimensional. Okay, that's all for pump part. So next week we will continue into the other turbo machinery in the turbine. So don't forget to fulfill your task, your piece in this week to consider your attendance also and also your assessment. So see you next week. Assalamualaikum.